Hello, I'm Norman Wahlberger. In this video, we want to move towards outlining a program for teaching young people trigonometry, starting from a solid base of geometry built up in the primary school years. So we have a possibility here of really revitalizing mathematics education in a very broad sense, really across the world. So it's a very exciting possibility, I think, that will probably really improve a lot of mathematics teachers as well as students. Okay, so a lot of work, of course, is required. We have to be prepared to look at this new alternative and sort of try to judge how this might work, how we might implement it, what aspects of it we should incorporate and others perhaps not. So new thinking is required. Probably some new textbooks and resources are in order. And we also need to retrain teachers to give them some familiarity with this new point of view. So lots of work to be done. It's not going to be done immediately in the near future, but it's something that we can work towards strengthening mathematics education for young people. All right, so the question before us is a question of maths education. How are we going to teach trigonometry? And we want to start by laying a foundation for that in primary school education with geometry. So let's just consider the stage up to year 9, okay? In terms of geometry, in terms of what young people are taught in primary and junior school. So very broadly, painting in very rough strokes here, here are sort of the essential aspects, or at least most of the essential aspects that I think we probably need to touch base with. And some of these will be probably pretty standard, and some of them may be a little bit novel. So I think a great place to start is with the plane. It's very geometrical, it's visual. Kids can play around with shapes. Basic shapes, triangles, squares, rectangles, trapezoids, circles, moving them around, getting familiar with them, and other related shapes as well. And then once we have a sense of shapes and we have sort of some fun playing around with those things, we can start talking about transformations and get students familiar with the idea of translation or reflection or rotation or even dilation. The idea that we can manipulate geometrical objects. And aside from the two-dimensional point of view, we should also let them know that there's a kind of underlying one-dimensional framework to a lot of geometrical objects formed by points and line segments and lines, and then also vectors. There's no reason why young people cannot be exposed to the idea of vectors. That's something that really ought to come earlier than it currently does. And so for us, a vector is a relation between 2 points. It's a relative notion, and as such, it's possible for this relative notion to equal this relative notion. Right, so the displacement here equals the displacement here. The two vectors are the same, even though they're in different positions. Okay, so it's very useful to get very clear, even at an early stage, the distinctions between points, lines, and vectors, and to prepare ourselves for a vector kind of orientation to geometry, which is going to end up being very powerful as we move further along in the educational stream. And now we can expose students to two beautiful theorems, the theorems of Pappus and Pascal, which are fundamental theorems for projective geometry, but we don't have to use those words. They're just theorems about lines and intersections of lines, so they're very amenable to direct investigation. And of course, we want to encourage that. And we won't go into details. If you're interested in these theorems and my approach to them, have a look at Elementary Math 12 in my series on K-6 education, which I need to do more of. But anyway, I do make the point there that I think these are really good entry points to the idea that mathematics has content encoded in theorems. A theorem is not something to be scared of. A theorem is a beautiful fact that has been discovered and that we can observe and validate and explore. But it's not entirely obvious. It's like a treasure that somebody has found. Okay, and these are definitely treasures, and students can get some appreciation for that mystery and magic of mathematics by seeing these theorems at an early age, even if we do not prove them. So we just give them to students and we let them verify the theorems in special cases so that they believe the theorems. And we leave to a further time the idea of actually finding a proof. That will come later. Okay, so then I think it's time to move to measurement. We want to introduce measurement into geometry, and I'm firmly convinced that in the planar situation, the best way of doing that is through area. Okay, area is the fundamental measurement, not distance, not angle, not anything else, area. And a really good way of doing that is through a piece of graph paper. And with a piece of graph paper, we can talk about numbers of squares. So we have a direct, immediate understanding of areas. This thing here has an area of 6. We can count 6 little squares. This thing has an area, well, it's half of the rectangle with area 3, so its area ought to be 1.5. And we can then move towards understanding and evaluating areas of parallelograms. Having done that, we can then move to Pythagoras' theorem, which is the most important theorem, not just in geometry, but also in mathematics. And we can express it crucially the same way Euclid did, in terms of quadrature, in terms of areas of squares built on sides of a right triangle. There's a right triangle. There's Q1, the area of the square built on that side. We can call it quadrants. That's a good name. Over here is another square with area quadrants Q2, and over here the hypotenuse has a square, its area quadrants Q3. And Pythagoras says that if this is a right triangle, then Q1 plus Q2 equals Q3. Okay, no sums of distances squared. Okay, nothing like that, please. Very important that students are shown Pythagoras using this diagram. These squares are absolutely critical. Okay, don't let them think that it's this distance squared plus this distance squared equals this distance squared. You want them to think about this area plus this area equals this area. And maybe you can calculate this area in terms of taking that distance and squaring it, perhaps, if the distance is kind of lined up nicely with your grid plane. But if it's not, like here, you may have to resort to indirect, alternate ways of getting at the area. It's not necessarily a distance squared. Okay, so that has to be done. Students have to see that, and they have to get an appreciation for a proof. They really should be able to go home to their parents and say, look, we've discovered how to prove Pythagoras' theorem. You move these things around, and this sum equals that sum. And it's fabulous. Okay, so there's two other kind of major things that I want to make sure that students have some exposure to before they get to year 9. And this is one of them, the area of a parallelogram in vector form. This is a crucially important formula that we've seen, right? We have a lot of experience for this cross product, but it's so elementary that a year 8 student can learn this very easily. So after we've experienced the Cartesian plane, have some familiarity with x and y coordinates. So there's the vector 3, 1, and there's the vector 0.7, 2.3, or whatever. Then we can talk about the parallelogram formed by those two vectors and the area of that parallelogram in the sense that we've been talking about previously. And then there's this beautiful formula that the area is AD minus BC. And it's actually a signed area, so that if you interchange the order of the vectors, then you get the negative of what you got before. This is a crucially important formula for lots of things. It's crucially important both in calculus and in vector linear algebra. So it's more than appropriate that students see this before year 9. And they can make calculations with it. The other thing that I want them to have some familiarity with are the conic sections, the ellipse, the hyperbola, the parabola, and of course this circle as a special case of the ellipse. And the best way of introducing those is just the same way that the ancient Greeks thought about it, the same way Apollonius thought about it, in terms of sections of a cone. So we move to a three-dimensional situation, talk a little bit about three-dimensional things, that's great. and some elementary things about three dimensions, in particular this cone, and slicing this cone with the plane, and what do you get? You get ellipses or hyperbolas or parabolas depending on the relation between the plane that you're slicing and the cone itself. And you can talk a little bit about some properties of these things, maybe how they figure in daily life. You can mention the fact that planets or comets go around the sun in elliptical paths or hyperbolic paths. Or in fact, actually almost parabolic paths is kind of possible too. But they have all kinds of other applications in real life, and these are interesting things. And these are the most elementary and fundamental kinds of curves after the lines. So as a natural hierarchy, once we're getting comfortable with lines, we move up to the quadratic situation embodied by these conic sections, these curves. Okay, so the students need to have seen them and be a little bit comfortable with at least some of their elementary properties. Okay, so now we come to the important years, year 9, year 10, roughly that period, where students they're moving into high school now, they've got some experience, they're going to move to more advanced things. In particular, they're going to start learning some trigonometry. And it's at this level here, really, where rational trigonometry can be introduced to students. And it's not something that needs to take 3 years to introduce, okay? You can introduce the essentials of rational trigonometry in 1 year. In fact, considerably less than 1 year, but you want to support it with lots of examples and applications and so on. So 1 or 2 years of rational trigonometry and they'll have it down very solidly. Okay, so a good place to start is with this Cartesian framework. I think that's a good place now to sort of navigate towards, first of all, and to get some familiarity with lines expressed algebraically. So for example, a line expressed by an equation like 2x plus y equals 2, and also an alternate form of a line, the vector equation of a line, given by something like this, where we're talking about a point, 0, 2, plus some multiple of the vector 1 minus 2. Note the somewhat novel combination of points and vectors. This is a very good idea, okay? To allow yourself to take a point, add a vector, and get another point. Makes sense because a vector is essentially a difference of points. So if you have a point and you add a difference of points, it should make sense that you get another point. Okay, so we have these two different ways of expressing a line. This is a very important kind of dichotomy about thinking about lines. And then we can get to the second most important formula, which is triple quad formula. Okay, the relation between the 3 quadrants is formed by 3 points on a line. There's 3 points, quadrants Q1, quadrants Q2, quadrants Q3. What's the relationship between those numbers? It's given by the triple quad formula. So students in year 9 can learn this. They can see a proof of it. It's a little bit algebraic. There's some algebra, some symmetry floating around. They can manipulate variables in a quite pleasant way. So they can learn a lot by studying this equation and the asymmetrical forms of it as well. Okay, and now it's time to introduce the heart of rational trigonometry, which are the various laws based around the notion of spread to complement the notion of quadrants. And I think it's reasonable for year 9 students to be shown a spread in a geometrical way, very much the same way I introduced it at the very beginning of this trig series, wild trig 1, 2, 3, 4. We were talking about the very foundations of trigonometry from just a naive kind of geometrical point of view. That's quite appropriate for year 9 students. Okay, so a spread between 2 lines, here's a line, here's a line. The spread between them is drop a right angle down, just like the Egyptians would have, and look at a ratio, but now a ratio of quadrances rather than a ratio of distances. The opposite quadrants divided by the hypotenuse quadrants. Pleasantly, it doesn't depend on where you drop this perpendicular down. It also doesn't depend on whether you drop it down this way or drop it in the other direction. So there's the spread between 2 lines. And then, then you have the foundations of trigonometry, all captured by this one diagram, a triangle with 3 quadrants as Q1, Q2, Q3, and corresponding spreads S1, S2 and S3. And we want to understand the relationships between these quantities. Okay, you all know what they are. There's the cross law, the spread law, and the triple spread formula. The cross law allowing you to calculate a spread from 3 quadrances. The spread law showing this basic symmetry between the ratios S1 over Q1 and S2 over Q2 and S3 over Q3. And the most complicated one, the triple spread formula, which is like the triple quad formula except it has an additional cubic term, which explains the relationship between the 3 spreads of a triangle. It doesn't take years for students to learn this. Okay, they can learn this in weeks or maybe months at most. Okay, and they can gain confidence by verifying this. You can actually exhibit triangles, real triangles in the plane. You can compute quadrances. You can compute spreads. You can check arithmetically that these laws are actually satisfied. So it's great practice for students to utilize their arithmetical skills. We've put the calculators aside, right? Under lock and key, no calculators allowed. The arithmetic is by hand, so students are practicing their arithmetic. They're working with fractions. They're working with interesting formulas, not just random kinds of things. They're actually trying to verify a formula. Here's the left-hand side. Here's the right-hand side. Are they equal? Yes, they are. Fabulous. It works. That kind of thing. And it's also really great for their algebraic skills because the way the formulas are expressed is algebra, right? There's these variables. So they have to learn how to manipulate expressions like this, how to move them around, how to rewrite these formulas in alternate ways, because there are other ways of writing them, and it's nice to have different points of view. Okay, so much that we can learn, and beautifully after we have done that, we really have the foundations of rational trigonometry, and that's it. Now you can go and solve lots of engineering and surveying problems. You don't need trigonometric tables now. It's beautiful. Okay? You don't need the calculator. Occasionally you might need to calculate an approximate square root, solve a quadratic equation. That's typically as complicated as it gets because these equations, quadratic equation sort of is the worst that it gets. If you look at this, if you know S1 and you know S2 and you want to calculate S3, it's a quadratic equation for S3. So this is a far cry from the usual story. And it's such a huge opportunity now to make mathematics education a more pleasant experience for so many students. Okay, but our Year 9, Year 10 students have a lot more energy and time at their hands. So what else are they going to learn? Well, of course, we also want to teach them about circles. But we want to put some space between the circle geometry and the rational trigonometry for a triangle that they've just learned. So no problem about putting the rational trigonometry aside, doing something else for a little while, maybe some algebra or statistics or something else, and now coming back to circle geometry, which is a different topic from rational trigonometry. Yes, there might be some connections, but that's not what we're going to emphasize. We're now going to study a circle. And, okay, there's much to be said about circles, but I think probably the natural things to start with are these two facts. First of all, Thales' theorem, which is really the oldest theorem about circles, which is that if you have a diameter of a circle, then that diameter subtends a right angle at every point on the circle. So in other words, you connect any point on the circle with these two ends of the diameter, and these two lines are perpendicular. So if AB is a diameter, then AC is perpendicular to BC. That's a beautiful, beautiful fact. And another kind of very lovely fact is one that we've talked about in terms of generalizing, that we will generalize, is its tangent radius theorem, we might call it, that if you have a circle, and you have a point on the circle, and you're interested in a tangent line to the circle at that point, that tangent line is perpendicular to this radius vector joining the point to the center of the circle. That the tangent to the circle at A is perpendicular to the radius OA. And this gives us a chance to talk a little bit about tangents to curves, which is an important idea. And if we know a little bit of Cartesian coordinate geometry, we can even aspire to writing down equations of tangent lines and verifying perpendicularity directly. Okay, so this is something that they can do and connects algebra with geometry. So we'd actually give a proof of this. It's not just something that we claim. They can see how algebraically it actually works. All right, now what about the area of a circle? This now is a very subtle and delicate point. Notice area in quotes. The area of a circle, and pi also in quotes. So now there's a question. Let's say we have our unit circle that we've already been discussing and students are familiar with it. And here we've put it in a box. We can see this box has side lengths 2, so it's a 2 by 2 box that has going to have area 4 in terms of our little squares in the graph paper. But what is the area of this circle? Well, that's an interesting question, but there's actually a more fundamental question, which is very important to enunciate this question. And that is, does the unit circle have an area, pi? Does it make sense to say, let's let pi denote the area of this unit circle? It's not at all so clear. So historically, this is a question fraught with subtlety. Okay? Certainly we can subdivide our square here into lots of little pieces, and we can start counting smaller squares inside and outside, and we can get some feeling for what the area ought to be or what it approximately ought to be. But can we actually somehow deal with the rounded aspect of the circle? The fact that this is actually round and it doesn't fit nicely into any one of these boxes that we're subdividing our basic square in. Or even if we don't just allow squares, but we are allowing general triangles, because we have a more flexible area formula for parallelograms or triangles. Still, the question is, can we apply that kind of linear formula to this curved situation? Well, that's a very, very delicate question. And there's such a temptation here for teachers, I know, to cheat at this point and say, well, look, obviously the area of a circle is well defined. Let's just define the area to be pi, and we'll assume that there is such a number out there. This is a huge assumption. Okay, it's a dangerous assumption as well. And in fact, it's an incorrect assumption. Okay, the answer actually is that the unit circle does not have an area in the usual sense. Okay, it's not the case that the area of a circle is well defined. That's the actual sort of reality of it. At least not defined as a number in the sense of a real number, because the theory of real numbers involves, as I've said many times, right, involves infinite computer programs that ostensibly run forever and whose output you only can access at the end of time. And this is more or less nonsense, okay? So if you stop before the end of time and actually get something finite that you can actually talk about, then you're not actually obtaining the area, you're obtaining some approximation. Okay, so it's a very subtle thing. But it's safer to adopt a point of view motivated by Archimedes thinking, who was the first person to sort of seriously investigate the value of pi. He did it, by the way, not in terms of an area, but in terms of an arc length, a circumference. But still the same kind of reasoning applies. That what you can aspire to do is to say, well, if this area did exist, if the circle did have an area, then it should be somewhere in between these bounds. Okay, that's the kind of thing that you can aspire to. But that already suggests that you have a flexible idea, that you're thinking, well, maybe there is no such thing as a precise area, that maybe area is only an approximate notion. What a powerful idea that is, okay? The idea that when we move from areas of trapezoids and triangles and rectangles to area of circle, we move from something that's exact to something which is only approximate. Okay? This is such an important idea. Okay? That we are necessarily giving up on the exactness that we have over here. That's just the way the life is, just the way mathematics is. There's nothing to be ashamed of in saying, well, we can talk about an interval. Or we can talk about something in this form, 3.1415926 dot dot. Notice 2 dots. I like to use 2 dots to mean that this is somewhere in the range between 3.1415926 and 3.1415927. Jack that one up one. So that's really specifying an interval, saying, well, something's happening in that interval. What exactly, we can't exactly precisely say, but it's something in there. That's a good way of thinking. That's an approximate way of thinking. It's an applied mathematical way of thinking. It's an engineering kind of point of view. It's very reasonable. But this is a subtle issue, and that's why this comes quite a bit later than the discussion of areas for primary school students that we had quite a few years before. Right? This is already year 10 kind of stuff now. So it's not so elementary. The students have to have more maturity. They have to treat this rather carefully and delicately, and the teacher has to be mindful of not distorting reality too much here. Right? We want to be honest with our young people. Nothing wrong with saying, guys, this is a situation where we have an approximate situation here. It's not an exact situation anymore. The question that we're asking only has an approximate answer. And closely associated to that discussion of areas of circles is the discussion of angles for a circle. Defining angles. Angles are approximate measurements on a circle. So the equal subdivision of a circle or a circular arc is only an approximate concept. As I've mentioned before in our last video, dividing a segment into 5 or 7 or 23 is not something that typically you can do exactly. It's something you can only do approximately. And the setting up of angles is necessarily therefore an approximate kind of measurement system. And again, we're not embarrassed or shy about explaining that to students. So when we set up the angular system, we're going to use the Babylonian system, 0 to 360 degrees. Okay? Radian measure is not going to be introduced at this point. Okay, we're not going to mention radians. Okay, angles, 0 to 90 degrees. We're going to have angles from 0 to 90 degrees to 180 degrees to 270. And by the time we get to 360, we're kind of back to where we started. And the main angles of interest, if you divide 0 and 90, there's 45, there's 30, and there's 60. And you bisect these, you get 15 and 75. And it's probably quite useful for students to learn them in terms of these multiples of 15 degrees. Multiples of 15 degrees is particularly amenable for a number of reasons. One of them is that, as I mentioned in my previous video on reticus, getting at 15 degrees is something that's not hard to do using ruler and compass. The other reason is that this divides everything into 24 pieces, which fits naturally with time zones and sort of geography of the Earth. So it's very useful for students to see subdivisions in 15 degrees. And I propose that that's what you might want to do. Okay, so once we have this kind of angles, and we tell students, like, this is something you can only do approximately. Okay, you can't do this exactly, but nevertheless, it's very important for astronomy. And you can talk about the importance of the historical connections with astronomy. And of course, we also need to mention this classical fact about angles of a triangle, that we can have an alternate system of describing triangles in terms of angles, where we use this system here to assign numbers of degrees to these vertices, in which case A plus B plus C is approximately 180. And notice that we're using this approximately equal sign because we're no longer in pure mathematics here exactly. Right? This is no longer a pure mathematics situation because the angles themselves are not, you can't get at them precisely. So we acknowledge that by using approximately equal. That's exactly what happens in practice. If you actually have a real triangle, then you end up with the angles only approximately, and in fact, you get a formula like this, only approximately true. That's actually what actually does happen. So we're going to touch base with this formula, but not in a big way, but students should be able to do a little bit of angle chasing because it's historically important and it has applications, no question, okay? So it's not something that we're going to deny. It's just that it's going to be rather secondary, and they're going to learn it separately from the rational trigonometry and more in the context of understanding a circle. Okay, so that's a great program for the geometrical side of Year 9, Year 10 level maths. In our next video, we're going to talk about what happens when we move to the senior level maths, years 11 and 12 roughly, and what happens there in the world of geometry, sort of building on what we've accomplished so far. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.